So I tried this out. I got an answer that works. There were problems along the way, but I did get to an answer that works. So I'm gonna try to reproduce that for you here with the problems and all, and kind of discuss what went wrong and how it actually worked out in the end anyway. So I'm gonna draw some before and after diagrams. So this starts off with a proton with I'm going to give it a mass of m, and it's going north, and the velocity is 2.0 times 10 to the 4. And in front of it somewhere is an alpha particle. The mass I'm going to make is 4m. It says it's 4 times the mass of the proton. And this one's at rest to start. So there is momentum before the collision. The momentum is due to the proton moving north. Okay, now after the collision. So it tells us the direction that the alpha particle bounces off in. So the alpha particle gets knocked, mass is 4m, and gets knocked in the direction of north 30 degrees east. And they don't tell us the velocity of it, which they would have if this were not an elastic collision question. They would have had to tell us the velocity here. But because they gave us one more piece of information here, that this is an elastic collision. I guess it doesn't actually say that, but we talked about in class that these subatomic particles, they make elastic collisions. That one extra piece of information will actually provide us with one extra equation, which means we can have one extra unknown variable to solve for. So for now, all I can really do is label in the angle. It's 30 degrees. And I'm going to label this this vector as v. I'll call this b prime. I'm going to use a for the original object that was moving, which was the proton, and I'll use b for the alpha particle. Okay. Now I'm going to draw the proton. So the proton will also get deflected in some kind of an angle. We don't know the angle of the proton, actually. And here's something that kind of went wrong for me. Since I didn't really exactly know which way it would bounce, I had to try to use an intuition and guess. And I guessed it was something along these lines, going northwest in some kind of direction. When I calculated the answer, it turned out that that was wrong. It actually ends up bouncing a little bit towards the south. It looks a bit more like that, but I didn't know that the first time I tried to do that. So I'm actually going to go and reproduce to you the way I started and how I kind of resolved that later on. Okay, so this angle is unknown actually, so I'm going to call that theta, and I'm going to label the diagonal arrow here VA prime for the velocity of the proton. Okay, so I got my diagrams done. I've got 4 unknowns actually. So 2 unknown final speeds, 1 unknown final angle, and I don't know the masses of these things. However, I know the relationship between them. One's 4 times as much, so that helps. That'll allow the mass to cancel out when I'm doing the equations. And a proton is about 1/4 the mass of an alpha particle, which is also called a helium nucleus, the nucleus of a helium atom, which has 2 protons and 2 neutrons, so it weighs about 4 times as much as a normal proton does. Okay, so if I have 3 unknowns, essentially 3 unknowns, in order to solve it, I'm likely going to need 3 equations. How am I going to come up with 3 equations? So it's going to be the conservation of momentum, but I'm going to analyze that in each direction, the x direction and the y direction. I'm going to define those. I'll say that east is my x direction. And I'll say that north is my y direction. So I'm going to start by looking in the x direction. So for my x direction, what I notice is that I have 0 momentum in the x direction before the collision. So, due to the conservation of momentum, my p prime total must equal 0 as well. Okay, my x momentum after the collision has to equal 0. So when I look at my after diagram, I've got an x component on each of those particles, and they're going in opposite directions. So I'm going to say that their magnitudes are going to have to be equal to each other, the magnitudes of those momentums. So I'm going to write it like this. I'm going to say the magnitude of momentum of particle A in the x direction prime, so after the collision, has to equal the same thing but for particle B prime. They're in opposite directions, so I'm saying their magnitudes have to equal to each other. Their magnitudes have to equal each other. And then I'm going to turn these momentum equations into m times v, mass times velocity. So for the left particle, the mass is m, and the velocity in the x direction will be the velocity a prime, and using SOHCAHTOA, it would be sine of theta. And equals, so the other particle, the mass is 4m, times the velocity, which will be vb prime, and the x component of that will be times sine of 30 degrees. So I have an m on both sides that will cancel out. I'll do a little more simplification. I know that sine of 30 is equal to 1/2. That's a special ratio. So when I do 4 times 1/2, I end up with 2. So on the right side, I'll have 2. VB prime. And on the left side, I'll have VA prime and sine of theta. So this here, that's going to be called equation 1. And you may notice that equation 1 has 3 unknowns in it. 2 unknown velocities and an unknown angle. Okay, now I'm going to look a little bit on my y direction. Okay, in the y direction. So same thing, conservation of momentum, this time in the y direction. So when I look at my before and after, my before diagram, I do have momentum in the y direction. I do have momentum in the y direction. That proton is going north. So I'll say that momentum total in the y direction has to equal the momentum total in the y direction after the collision. So the total y momentum before has to equal the total y momentum after. So for the total y momentum before the collision, it's just the proton. So I'll do mass times velocity. So the mass of the proton is m. And the velocity of the proton is 2.4, so 2.0 times 10 to the 4. So I'm actually going to just expand that out. That would be 20,000. My brain's just a little more comfortable with integers. That's not too many zeros to write down, so I'll write them down. After the collision, I've got two particles. Both of them have a y component in their momentum, so I've got to write an expression that adds the two together. So I'll start with the proton. So the proton's y momentum will be mass times velocity times, to get the y component, I times it by cosine of theta. The y component's the adjacent side in the diagram I drew. So that was for the proton, and now for the alpha particle, the mass of this is 4m, velocity b prime, and cosine of 30 degrees. All right, so that's the second equation actually. I can simplify that a bit. There's three terms here. They all have m in it, so that cancels out. So this simplifies to 20,000 equals velocity of A times cosine of theta plus 4 times cosine of 30. That is a special angle. It makes root 3 over 2. However, I'm just going to leave it as 4 cos 30. I'm going to write it as 4 cos 30 times velocity of b. Okay, so that is equation 2. And it has the same three unknowns, velocity a prime, velocity b prime, in the angle. So I've got two equations, three unknowns. Usually that's not enough equations to solve for three unknowns. I'm going to need the third equation. And that third equation is going to come from the fact that it's an elastic collision. That's going to provide us with equation number 3. If we know that it's an elastic collision, then the definition of that is that the kinetic energy is conserved. So kinetic energy total equals kinetic energy total after the collision, so prime. That's what an elastic collision means. So I'll analyze before and after. Before the collision, do I have any kinetic, well, what is my kinetic energy? It's all due to the proton, since the alpha particle is not moving. All the kinetic energy is due to the proton. So I'm going to use half mv squared, half the mass times the velocity squared. So that would be 20,000 squared. So that's my starting kinetic energy. And my ending total kinetic energy, both particles have kinetic energy. They're both moving. So we'll start with the proton. That'll be half mv squared, so VA squared. And now I'll add the kinetic energy of the alpha particle, which has a mass of 4m. So the kinetic energy formula will be half times its mass of 4m times its velocity vb squared. So this simplifies. I can actually cancel out half m. Every term has half m in it. So divide both sides by half m. Gets rid of those half m's. And leaving me with, I'll expand 20,000 squared. So I got a 2 and 4 zeros squared. So that'll be 4 with 8 zeros. So I guess that would make it 400 million. Okay, so that's what I come up with. And that is equation 3. Equation 3 has 2 unknowns. Doesn't have all 3 of them in it. However, it does have 2 of the unknowns that were in the other 2 equations as well. So at this stage, we have what we call 3 equations in 3 unknowns. And theoretically, there's ways to solve that using substitution, elimination. Which I'm not going to do. Obviously, I'm not going to do that. It's a lot of writing, a lot of work, a lot of having to keep track of things. If I try to do it, I'll probably forget to write a plus sign or a minus sign or a sine or a cos. I'm going to forget something. So what I actually did, which is on the next slide, is I typed all 3 of these equations into Wolfram alpha. I used capital A for the velocity of A, I used capital B for the velocity of B, and I used X for the theta there. So I'll show you what that looks like, and also the problem I run into when I do that. So at the top here, you'll see that that's what I typed in. Okay, so I use the asterisk to do multiplication. When you do sine and cos, make sure you put the thing in brackets, like the angle needs to be put in brackets. Use the word and. So after I type my first equation, use the word and, meaning I'm going to talk about my second equation. And I have it again because and then I type in my third equation after that. That 400 million equals a squared plus 4b squared. Okay, so then I hit enter, and a bunch of stuff shows up. I just cut and paste some of the stuff that shows up, not all of it. One thing that shows up is the input. So this is what you can look at to see if it looks right, if the equations look like how you meant them to look like, which they do. One key thing to check for is there's a degrees here. If there's no degrees there, they're going to do things in radians. And I actually typed in degrees. You can go to extended keyboard and choose degrees to make sure it reads the angle as degrees. Okay, so that looks good. It has the three equations I want. And then now the good stuff are the solutions. There was some stuff in the middle here, but I jumped down to the solutions. So it's saying there's 4 possible solutions to this. And 3 of these are going to be inadmissible. So the first one is inadmissible. This is saying that A, which is the proton, just comes back at negative 20,000. So that was the starting velocity. Now it's saying it's coming straight back. Well, no, it's not going to come straight back. So that one doesn't make sense. It's inadmissible. The second one is also inadmissible. This is trying to say that A is 20,000, which is what we started with, and B is 0, which is at rest, is what we started with. And so this means they didn't hit each other. This is the solution that corresponds to the particles just missing each other completely. And yeah, everything's still conserved. All the momentum and all that is still conserved, but they kind of just missed each other. So that's not the solution we're looking for. The other 2 solutions look pretty much identical, except one of them's got a negative sign. It's a negative answer, and that's going to be inadmissible. Because when I was writing the equations out, you may have noticed that I was working in terms of magnitudes. I was typing magnitude of VA prime on all 3 equations. All 3 equations I did that. And magnitude means the size of something. It's always should be a positive number. And this is giving us a negative value for A. So that's not the one we want. This last one, this is our solution. So the velocity of A, the proton, ends up being 14,422 meters per second. I'll have to do sig digs, but not worry about that for now. It's saying that the velocity of B, which I had it as the alpha particle, is 6,928 meters per second. And here's where it got messy, the angle. The angle. So what the heck is this saying about the angle? It's saying that it's 2 times bracket pi, that 3.14159 figure, that's pi, n plus 0.925916. N is an integer. That whole expression, that's actually trying to communicate all possible angles it could be, which it can, if you get an answer of a certain angle, you can always continually add 360 degrees to it, and it arrives back at the same position. Add 360 degrees, add 720 degrees. All of these angles point the same direction. So that's what this business with this n in this thing, in this 2, that's what it's all doing, because 2 pi radians is 1 full revolution. Okay, so I'm going to kind of just ignore all that. N's allowed to be any integer. So let's just choose 0. We'll choose n to be 0, which makes that term go away. So now it's telling me that x is the angle. I didn't bother to try to type in theta. I just typed in x. They're saying that theta is going to be 2 times 0.925916. So I'm going to double that figure, which gives me approximately 1.8 1.85 approximately. But the problem is this is in radians. It's 1.85 radians. It's not in degrees. So I had to convert that to degrees. How do you go from radians to degrees? You divide it by pi and multiply it by 180. Divide it by pi and multiply it by 180, which turns out to be 106 degrees. Turned out to be 106 degrees, which doesn't make sense because in the way I drew my diagram, I'm gonna move on to the next slide actually. The way I drew my diagram, I had the alpha particle going off at 30 degrees. That's because that's what the question said. I had my proton going off at some angle here. This was my angle, but my Wolfram alpha is saying that this angle is 106 degrees. So what does that mean? Well, that actually means that I had it pointing in the wrong quadrant to begin with. So if I go from the vertical line, if I go 106 degrees, that's more than 90, it's going to end up somewhere over here. Okay, so this is 106 degrees, which means the proton actually ends up going a little bit towards the south. So if I subtract 90 degrees from 106, I get 16 degrees. So my final answer would be that the velocity of the proton prime after the collision was that 14422 number. I'll do sig figs now, so 1.4 times 10 to the 4 meters per second, and it's actually west 16 degrees south. The velocity of my other particle, they gave 6,928, so with sig figures, 6.9 times 10 cubed meters per second. That one, we were told it goes north 30 degrees east. And that's it. Okay, so that would be the answer to this. Now, I had to double check because when I set up those three equations in the first place, I set up those equations assuming my angle was acute, assuming that my arrow pointed in this original way. So what I had to do was check if this answer is actually right. I won't show you the steps there, but I double checked that the x momentum does end up equaling 0 if I plug in these numbers. I double checked that the y momentum does end up adding to the initial y momentum. And finally, I double checked that the ending kinetic energy does equal to the starting kinetic energy. I had to do all those checks because of that issue with having that arrow drawn in the wrong quadrant to begin with. But it turned out that this is right. It passed all three of those equations. So momentum is conserved in both directions and kinetic energy is conserved. It's a elastic collision.